So again, thinking about the flow directions, right? So there's actually stream underneath the end CSTR, which we name it as n-1 stream. And the stream above the end CSTR by definition is end stream, right? But as you can see from this double-sided arrow, flow can come into the NCSTR from the top, or it can go out from the top of the NCSTR. As first, the flow can come into the NCSTR from the bottom, or it can leave NCSTR from the bottom, right? So there's actually directionality that's really important to account for in our model, because flow direction can change, right? Depending on the pressure difference or whichever condition that's happening inside the column. So to account for this, we actually define so-called pseudo volumetric flow rate. This is nice because we are able to always use this volumetric flow rate regardless of which direction the flow is. So for instance, VNT is the volumetric flow rate that's coming out from the NCSTR, right? If it's positive, then you're just adding two positive numbers divided by 2, so you just get the positive number. So when the flow out is positive, you get the positive pseudo volumetric flow rate, positive, right? And if you take a look at this though, with positive Bn, you're subtracting absolute value of positive number minus positive number, so it's 0, right? So Bn minus is 0. So the nice property of we always consider these pseudo volumetric flow rates in pair, right? These are the pseudo volumetric flow rates, positive and negative pseudo volumetric flow rates for the NCSTR. And the main takeaway here is that the positive pseudo volumetric flow rate and negative pseudo volumetric flow rate works together, right? So if one is, so first of all, they're always positive, or I say non-negative, and if one is positive, then the other one is 0, right? So you can kind of see that, right? So for instance, if volumetric flow rate coming out from the NCSTR is negative, right? Then what happens? Where this is absolute value of negative number, so that's positive, but then you're adding a negative number, so your positive pseudo volumetric flow rate becomes 0 when this actual volumetric flow rate is negative, but then your negative volumetric flow rate becomes positive, right? Because the absolute value of negative volumetric flow rate is positive, but then you're minus negative volumetric flow rate. So minus is plus, so and you're divided by 2. So basically you will have positive negative pseudo volumetric flow rate and 0 positive pseudo volumetric flow rate when actual flow rate is negative. So these are really nice. It allows us to write our mass balance independent of the flow direction. So actually, that's the main advantage, right? So that's why we adopted this formulation in our work. So you can almost think of this flow terms, right? As the concentration of the NCSTR times positive pseudo volumetric flow rate, and the minus the concentration of the CSTR above, right? N plus 1 CSTR times the negative pseudo volumetric flow rate. So this actually describes the molar flow rate associated with the end stream, right? So end stream right here. So the molar flow rate associated with end stream can be written independent of the flow direction by using this notion of pseudo volumetric flow rate. Because when this one is positive, this one is 0, and this one is positive, that one is 0. So it's really important, right? So flow is starting from and going to, right? So this concentration has to be always the concentration that where the flow starts, right? Because that's what the concentration of the stream would be. And once we are able to write these molar flow rates independent of flow direction, we can plug it back to the first and the second term in equation 3. Then we're able to finally do some algebra and derive this equation. So rate of change in the gas phase concentration of species I in NCSTR at time t is equal to this is basically the scaling or the factor for accounting for the volume rate. But then we actually have this convective flow terms. So positive pseudo volumetric flow rate from the n-1 CSTR times the concentration of the I species from the n-1 CSTR plus the negative pseudo volumetric flow rate times the concentration of the n+1 CSTR, the I species concentration. And then you can also have minus and then the negative pseudo volumetric flow rate going out to the negative n-1 CSTR from the n-CSTR, and then positive pseudo volumetric flow rate going out from the n-CSTR to the n+1 CSTR. So the corresponding concentration would be that of the n-CSTR, and then you just have the net reaction term. So this equation holds true for each species, for all species for all CSTRs, right? So that's the mass balance for the gas phase concentration.